My name is Tomasz Gromadzki. I am software architect and PMDK team, Intel Optane Group. My work is mainly related to the implementation of persistent memory in distributed solutions. We call it remote persistent memory, RPMem in a short form. And this is the topic I'm going to talk to you about today. I'm going to start my presentation with an overview of remote persistent memory technology. I will show how it is designed, where remote persistent memory can be applied, and the benefits for applications that use it. Next, I will demonstrate the software that PMDK provides to support the easy adaptation of remote persistent memory in end-user applications. Finally, as the library is delivered with a benchmarking environment, I will end the presentation with real performance numbers. I hope this will encourage you to think about new areas where persistent memory can be applied. Remote persistent memory is built on the top of two technologies. Persistent memory, for example, Intel Optane persistent memory, and remote direct memory access, RDMA in a short form. RDMA is a technology that allows direct memory access from the memory of one computer into that of another without involving either one's operating system or even CPU. We can use it for persistent memory because it is a memory. RDMA has already been identified as a solution to improve performance of traditional storage replication. But we can see something completely new in terms of remote persistent data access performance when we put RDMA and persistent memory together. Why is it so fast? The reason for that is a purely hardware solution implements RPM data transfer. Software is only used to initiate and complete the transfer. You have at least two benefits in one solution. It is very low latency, and what seems to be important as well, we save CPU power. Pulling all these things together, remote persistent memory technology means low latency and low CPU cost of remote persistent data access. What is usually done in several steps when you would like to process persistent data on a remote node now can be achieved with one step. You may think, okay, this is a synthetic benchmark, but what about real applications? Yes, you have an excellent example. Oracle Exadata X8M is the most spectacular design solution that utilizes remote persistent memory and expose performance improvements, mainly due to RPMem technology. You can see similar performance improvements up to 10x from non-PMem solution to solution with remote persistent memory deeply embedded into Exadata system. Let's take a look at another database example, more generic one, and traditional transaction processing in a distributed environment. The transaction starts at a specific node and generates a lock increment. This increment has to be replicated to another node and applied before the transaction is completed. Otherwise, the increment from the volatile memory may be lost on power failure. And only then the transaction is complete. The transaction handling can be implemented in a different way when PMem is used. In this case, the transaction will also generate a lock increment, and it is also copied to another node. But we can end the transaction as soon as the data has reached the remote node because the lock increment is persistently stored there. Change on the remote node may be applied asynchronously. We have seen so far what benefits we get thanks to RPMem and have some information where performance improvements come from. Now, let's move on to the details of the technology and see what happens underneath. It should not be surprising that remote persistent memory access shall follow similar rules defined for local persistent memory access, and in fact, it does. Storage Network Industry Association standardizes so-called software persistent memory programming model. When writing data to persistent memory, for data to be considered persistent, the software is responsible for flushing data from CPU caches to the persistency domain. Once the CPU caches are flushed, the platform guarantees the right data is persistent. A similar solution is used when writing data to remote persistent memory. The procedure starts with an ordinary write using the write service of the RDMA protocol. We can use the write service because persistent memory is seen by RDMA network interface card the same way as regular DRAM. But we have to consider that RDMA write response only provides information about delivering data to the remote system, but doesn't guarantee its placement in the persistency domain. As the persistent memory programming model states, the application will need to execute the flush to ensure the data has been moved to the persistency domain. So, how do you issue a flush across the network? With existing RDMA protocol, the RDMA read is used for that purpose. The RDMA read forces any write data operation to be finished before the RDMA read can proceed. We owe this behavior thanks to the ordering rules of both RDMA network and PCI bus. We use the RDMA read, and RDMA doesn't have a separate service dedicated for data flushing so far. But the work is underway to develop a separate protocol services dedicated for this functionality. Now that we understand how RPMem works, let's look at how easily we can use remote persistent memory in the application. The hardest step seems to be acquiring the equipment. But when we manage to complete the server with persistent memory and RDMA network interface, we can start the RPM adventure immediately. We do not need any new technology. We use something that is already on the market for several years. The software we need is available on virtually all Linux distributions. There are many ways to access remote persistent memory from your application. libfabric library, libIBverse library, or RDMA-based reliable datagram sockets kernel module all provide suitable API. For many potential users not familiar yet with RDMA, they are not easy to use. It is where the new Remote Persistent Memory Access library comes, the librpma library. The library has been built to support the quick and easy RPMem technology integration, especially in areas on our applications where RDMA hasn't been used yet. The library provides an easy-to-integrate memcopy-like API with minimum dependencies to other modules. The API is designed to hide RDMA complexity, but still gives considerable flexibility on how persistent memory and RDMA can be used. The easiest way to see the library capabilities is to look at distinguished API functions groups. There is a set of functions for connection establishing, monitoring, and shutdown. Function for remote persistent memory reading, writing, and flushing. The library API also supports messaging based on send-receive RDMA services. Our messaging can use persistent memory as message data source and destination. There is a set of functions for memory management, and the API is ready to work synchronously and asynchronously, and can be easily integrated with select or epoll or similar kernel mechanism. Finally, the library architecture is prepared to support new RDMA verbs like atomic write, verify, or flush, as they will become available in the hardware. I'll show you briefly how easily you can perform RPMem transfer using the librpma library. This example will transfer a kilobyte of data from initiator node to the target node. Before you can perform the transfer between nodes, you have to register memory entries you want to perform the transfer. Every memory registration covers a memory region starting from a specific virtual address, F, and of a specific size. Every memory registration has also specific usage. In this case, the memory registration on the initiator node will be used as a data source, whereas the memory registration on the target node will be the data destination. Moreover, the second one also must be flushed after the write operation to guarantee written data persistency. We mark it flushable with a flush of a specific type according to the type of memory. The memory registration API call, when succeed, will create a memory registration object, which would later be used to perform operations. You have to do memory registration only once for a given memory ranges. The rest of the process is done entirely on the initiator node. First, you must perform a write operation. You must provide two memory registration, source and the destination one, for the operation. For each of the provided memory registration, you can independently set an offset from which the operation will start. For the operation, you have to show how many bytes will be transferred and where you expect a completion from the operation. In this case, I prefer a completion to appear only on error case. There is no visible action so far on the target node, at least from the software point of view. So, secondly, you must perform a flush operation to guarantee the data persistency on the target node. So you want to flush the memory registration you have just written, starting from the offset provided for the previous operation. And you want to flush the whole region being written. You have to choose the type of flush you want to perform. In this case, it is a persistent flush. And you have to choose, and unlikely to the write operation, it's good to have the completion for the flush, just to be notified when the data on the target node is persistent. The user-provided identifier will allow you to recognize the completion of this specific operation. After the flush, you have to wait for the completion using another straightforward API calls. And that's all. Please observe that there was no software action on the target node. So this way, we have made the first RPM operation sequence, and the data target node is persistent. Okay, let's start one more from this slide.
Okay,
my fingers are too nervous.
Okay, no worries. Just do a 5-second countdown whenever you're ready.
Yes. Thank you. 5, 4, 3, 2, 1. That was a part of one of the examples delivered with the library. You can find this one and many more in the library repository. They are organized to guide you step by step from the most essential and straightforward operation like connection setup via different memory operation like reading or writing to the most advanced operation like multiply connection handling. We built our examples in a way to be easily adopted into remote persistent memory tutorial. The library is fully open source. You can easily access the documentation and the source code. I want to emphasize that you do not need a dedicated server with persistent memory, and you do not need an RDMA network to start working with the librpma library. The desktop Linux environment is the only requirement to run all examples available in the library's repository. We are also open to your contribution. As soon as you set up your development environment, you can look at GitHub issues that compose a list of still to be implemented features. The librpma library is a core of the development environment that PMDK team proposed for remote persistent memory handling. But many people ask about remote persistent memory technology performance and how the application can benefit from it. Together with the library, we have developed benchmarking environment for that purpose. librpma FIO engine, together with benchmarking manuals and a set of scripts, allows everyone to measure RPMem performance in the various configurations. I especially encourage you to read the documentation and learn how to build and configure benchmarking environment. Remote persistent memory data path is very long, and many different software hardware components are involved in data processing. That causes remote persistent memory performance to be very sensitive to different configuration parameters like BIOS settings, PCI bus settings, RDMA network interface cards parameters. So the benchmarking toolsets cover all benchmarking steps from data collection via partial data analysis to complete performance report creation. You do not need to wait for anybody to provide you performance results. You can run benchmarking process by yourself. All that is needed you can find in the librpma repository. So let's find a look at how efficient RPM can be. I'll show you a couple of numbers collected on Intel servers equipped with Intel Optane Persistent Memory 100 series, 256 gigabits DIMMs, and connected back-to-back with 100 gigabits RDMA interfaces. Let's start with remote write operation. You have already seen some results at the beginning of this presentation. But what you could see in details is that RPM write latency seems to be very predictable and stable. The bigger data chunks are used, the closer to the remote DRAM performance we are. And what about bandwidth? The RPM write scales very well, but at the same time, it can saturate network bandwidth easily. As you can see from the plot, we need only 4 parallel jobs to saturate a 40 gigabits connection. For 100 gigabits connection, we need only 16 parallel workloads. It shows how efficient it could be and how important it is to build your solution carefully to avoid network congestion problems. So what about read operation? The speed of the read operation of our remote persistent memory is comparable to one from DRAM. And there are even use cases when we see that RPM performance exceeds what can be achieved with remote DRAM. Persistent memory may serve remote reads better than DRAM because it's solely dedicated to the user application, where DRAM is dynamically shared between various processes and the operating system. So if you want to run your own benchmark, you could reuse configuration that PMDK team used for performance results just presented. And now pulling all the things together, RPMem is one of the most efficient remote persistent data access, especially when low latency is expected. It's mainly due to RPM exposes minimum software overhead. There is already software solution and software environment to build RPM solutions on the top of well-documented and seasoned technology like RDMA and PCI. You can find several places on the internet when more information is available, including white papers and blog posts or PMem.io. And finally, when you start reading Programming Persistent Memory book, do not finish until you reach a chapter about remote persistent memory. So that's all of my talk. I hope you enjoy it and learn something. And I hope it will encourage you to think about new areas where persistent memory can be applied. Thank you for your attention. Now I'm happy to answer to your questions.